Hello Izmir 2022. This is Moji Haydari from the Audio Information Research Lab at the University of Rochester, New York, and this video covers our singing beat tracking with self-supervised front-end and linear transformers project. In this paper, we address singing voice beat tracking, basically tracking beats of singing voices without the presence of musical accompaniments can find many applications in music production, music processing, music studies, interactive systems, etc. The main challenge of singing voice beat tracking is the lack of strong rhythmic and harmonic patterns that exist in complete music pieces, which are important for music rhythmic analysis in general. It makes singing voice beat tracking a demanding task even for human listeners. On top of that, in case of singing without music accompaniment, the probability of having tempo fluctuations and local beat shifts is higher. So in this paper, we introduced the singing voice beat tracking as a novel MIR task. We proposed two strategies to create annotated datasets for the task using pre-existing datasets. We propose a novel evaluation gem that can account for phase ambiguities. And eventually, we propose two neural networks for the task leveraging pre-trained speech self-supervised models and linear transformers. In order to create vocal beat tracking datasets, we obtained singing tracks of beat tracking datasets with pre-existing beat labels and beat annotations of source separation datasets with pre-existing vocal stems using DMUX source separator and BeatNet beat tracking respectively as follows. Also, RMS filter removes big chunks of silence between singing parts. So here are the neural network structures that we propose for this task. The left-hand side model uses a weighted sum of all layers of pre-trained wave-LM self-supervised speech model to calculate the feature embeddings. The middle one uses the outputs of Distel-Hubert teacher-student model to obtain feature embeddings, and the right-hand side model employs the spectrogram representations that are used in conventional beat tracking models as the input features. All models take advantage of the same linear self-attention networks to fine-tune them for the task. So the evaluation table includes three baseline models and the proposed models results. It also includes the phase-inclusive evaluation gem for the proposed models, where the results are the maximum of the detections and the 180-degree phase shift of them. So several interesting observations can be made. First, all of three proposed models outperform three baselines by a large margin. This confirms our hypothesis that vocal tracks show very different patterns from complete songs, and the baseline models that are trained on the complete songs do not perform as well as the proposed models that are trained on the vocal tracks. Second, the two proposed models that leverage wave-LM and Distel-Hubert speech self-supervised learning features improve over spectrogram by a large margin. This shows the significant advantage of using feature embeddings learned from the speech data and suggests that this advantage is even more significant than training on the vocal tracks. So let's watch a demo of the model performance.
I've paid my dues time after time. I've done my sentence but committed no crime. And bad mistakes I've made a few. I've had my share of sand kicked in my